Just wait for a
Hello.
minute and we'll start. I will let you know.
Okay.
I will let you know.
Okay, sir.
Yeah.
Okay, sir. Sure, sir.
So, Dr. Anurag, maybe we can start today's session on demo of TEM. Please, you may
Yes, sir.
please begin. Yeah.
Uh, so welcome to all of you for today's demos on HR-TEM, high resolution transmission electron microscope. So today we'll show you what we do here using the HR-TEM and what type of analysis we can do. And we'll show you like TEM imaging, HR-TEM imaging, and SED imaging, and ADEX. So if time permit, we'll show the all of the things, how we'll do the experiment, how we'll get the results, and how we interpret the results. Okay, so before starting the things, what we do here, so let's talk about some small basics of the TEM. So TEM is basically electron microscope. So obviously, first thing will come in our mind, why we need the electron microscope. Instead, we have a optical microscope. So obviously, we know electron microscope has very high resolutions in order of in some few angstrom. Okay, so obviously, before talking more detail of the TEM, I would like to say why. Obviously, I'm talking about the transmission electron microscope. So we have electron beam and some electromagnets and some setup for the imaging type system. Okay. So before this is a demo class. So I'll show you the each instrument parts of the instrument one by one. So let's take a small tour. So you can see this is a big column of the tent, right? And these are the some electronics part of the TEM machine. And here you can see this is a transformer type setup to provide the very high potential to get the very high accelerated electron beam, right? And inside that, we can show you the, uh, this is the, please come. This is the chiller part and other electronic parts and UPS parts of the TEM machine. So please come. So if you see the monitor, so we can show you the schematic of the TEM column. Here we can see the electron gun, okay, and here we can see the right now it is on. It is on. So right now very high voltage, which is 200 kilovolt, okay, and the emission current is around something micro 141 micro ampere current it is producing now. So the machine is ready to do the HR TEM imaging. Okay, so and this this monitor we will use to see the actually this is controlled by the computer camera. So we'll use for the imaging purpose, and this is for the controlling. Okay, of the TEM. So shall we start, Nindu? So we'll fill the liquid nitrogen in the column. Hmm. Tally. Okay, so we are filling the liquid nitrogen in the column. This is the essential part before loading the sample and doing the taking the image. So it will take time around 2 to 3 minutes to settle down. Meanwhile, I will load the sample. Actually, for the imaging, our sample is kept on the very thin sample is required. Okay, very small amount sample is required. And this is a very tedious task for the sample preparation and loading on the sample grid. So in the TEM, what we do actually, we use the copper grade, which is copper grade, and a thin carbon film is coated on it. Okay, here you can see this is the copper grade. Sample is already, है ना? Okay, sample is already kept on the copper grade. So we will use one grade, and here you can see this is the raw type shape. This is a sample holder. Okay, so we'll load the grid on it and we'll insert this sample holder inside the column. Okay, so you have to do this very carefully so that carbon film should not be broken. So I'm holding it very carefully. Okay. Okay. So grid is loaded, and I'll fix it on the holder. Okay. Now it is done. So this is a uh, single tilt holder. So I'm ensuring whether it is properly fixed or not by giving small jar. So it is perfectly loaded. Now you can see this one is the sorry. It will take some around 1 more minute, I think, to settle down and take it out. Okay. Okay, actually we can put actually in the chamber, right? Okay, so I'm opening the chamber part. So here you can see there's variety of holders are available, automatic and manual, single tilt, double tilt. So we are right now we are using the single tilt holder. Okay. So here we will insert so there is procedure to insert the holder inside the very high. So right now the column is in a very high vacuum. Here we can see the variety of V1, V2, these are the walls, these are the chambers, different chambers. And gun chamber, they have a pressure. Here you can see. Okay. So now this inside the specimen chamber. Okay. So right now I'm in the chamber. So I'm inserting it carefully. So there is a locking screw. I'll keep inserting inside. Okay. So I have to hold it. So what will happen after inserting the holder inside the specimen chamber? Right now it is not in the column. Okay. So we'll wait because right now is nitrogen gas is purging inside the specimen chamber. Here you can see V8 valve is open, nitrogen is purging. Okay. After it is completing the purging of the nitrogen gas, then we'll start pumping and we'll start creating the rough vacuum. After that, we'll create the high vacuum. So that we'll able to insert the whole sample holder inside the column. So here you can see now nitrogen gas purging is completed now. So now we can go further. And here this is also almost completed. I'm closing this one. Okay. So now I'll select I have to tell the machine what sample holder we are inserting. So I'll select the sample holder here. Here you can see. Please select some holder data. So variety of sample holder is given, but we are inserting single tilt manual. So I'll select that one. Okay, single tilt holder, this one. Single tilt holder, okay. And I'll click on the pump. Okay, so whatever the nitrogen is filled inside the specimen chamber, it will vacuum out. It will take it out. Okay, so it will take around 4-5 minutes, and the pumping here you can see in the specimen chamber. You can see the pumping is started, and this will pressure will reduce. Okay, see it is showing value. It is showing in term of current. Okay. So it will go down. After that, we'll able to insert the holder completely inside the column. So it will take time around 2 to 3 minutes. So so as we know, if you see the if I talk about the resolution of this TEM, so we are operating at around 200 kilovolt. So corresponding de Broglie wave will be around 2.5 picometer. I'm telling picometer, 2.5 picometer. Okay, so which is very small. Okay, and if you see the resolution, it will theoretical resolution by using the relay criteria, we will get around 0.02 nanometer theoretically, but due to aberrations and some limited, we cannot make the perfect electromagnets. So practically we'll get the around 0.2 nanometer, that is 2 angstrom of the resolution, and we can magnify it up to we can go up to 1 million. Okay, this is the advantage. Right now it is set on the 800K. We'll reduce it. Okay, this is the magnification. Right now it is showing 300K. Okay, so usually fourth thing usually we do here. First for that first is the TEM image. Okay, second one is the selected SAED, selected area electron diffraction, and third one is the HRTEM, high resolution image of the particles, and which is atomic resolution obviously, and the fourth one is the EDEX. Okay, for the elemental analysis. So right now it is specimen chamber pressure is right now 39. I'll wait up to 33 microampere, and then I'll insert the specimen chamber completely. So here you can see the 3 monitors. This is for the TEM column itself, and they're controlling. Okay, this monitor is for the camera for capturing the image. We'll see the TEM image, HRTEM image, and set patterns here. Okay, and this monitor we will use for the seeing the EDEX analysis. So we'll run EDEX software on this monitor. Okay. So these three different and variety. Here you can see the different panels, imaging Z, Y, X, shift Y, and scroll. We will scroll the image. I'll show you what are the roles of these knobs and switches. Okay. This is for beam. This is for here. Here you can see this one is. I'll open. If you see here is the fluorescence screen where the obviously if you see the structure at the top you will find the electron gun, right? And here in between a variety of the electromagnet lenses, condenser lenses, right? And here we have here we have the here we have the sample specimen chamber and the column in between. Here we'll insert the here we'll have the copper grid or sample, right, on which electron beam will incident and it will transmit, okay, and will incident on the camera or fluorescence screen here, and here image will form. So it is the 35 right now. After reaching the 33, it is decreasing. So after reaching 33, I will able to insert the specimen chamber. So basically, TEM imaging is electron. See, when the electron interact with the matter, so multiple things is happening. If you see, you will get the some electron will scatter, right, elastically or some inelastically, and secondary electron emission, right, back scattered electron emission, agar electron, X-ray, multiple thing is happening, right? But the primary thing is the sample thickness is very small is required. Okay, very thin sample is required. So sample preparation is very tough. For the this is the disadvantage of TEM. So very expertise is required to prepare the sample, and grid is also quite costly and very sensitive. So this is one major disadvantage. And okay, so I think in 1935. So it takes time to do the experiment. It takes almost whole day for the one sample to do all the analysis. 3 to 4 hours, something like that. It's now 34. It is reaching around 33. So TEM imaging is we are taking from the elastically scattered electrons, and the image is formed is like a mass scattering of elastic electrons, and due to their mass and thickness, and if the thickness is high, so electron will not able to transmit, right? So image will be dark. The contrast will be formed if there is space, less thickness. So we will see at the bottom brightness, electron will able to transmit. So something some image will form accordingly, depending on the thickness, mass variation or thickness variation. So right, 33, it is now moving around 33, 34. So we can insert further. So it will, okay. So let's start inserting further. Okay. Now I'm rotate and it is going inside automatically due to pressure. So folder is inserted. Here you can see the electron beam can be incident on the grid. Here we can see the yes, this is the electron beam. We'll open the shutter beam ball and it will incident on grid and it will go down the camera this side. Okay. So I'm closing this chamber. Okay. So now the thing is ready. We are ready to take the images, TEM images. For that, we need to turn off the lights so that here fluorescence screen will. So for that, we need to turn off the whole light, room light. Okay. So if you are able to see, is it visible? Fluorescence screen, white, something like. Okay. No, I'll turn on the beam. Then you'll be able to see. Right. So I'm turning on the beam. Okay, right, not in magnification. So is it visible? Green sphere, I mean circle. So I'm going to low magnification and increasing the brightness. And I'll insert the one aperture inside. Okay. Oh, okay. That's why it was not working. Okay, now I'm inserting 200 micrometer size aperture. Now again I'm turning on the beam. So here you can see this is the if I reduce the magnification, will now you can see the grids and mesh. Is it visible? Please confirm. Anyone? Hello? Am I audible? Nobody is responding. No issue. Okay, so at the low magnification of 600 something thousand, we can see the grids and meshes. Here you can see dark patches on the here, bright and dark. So here we have to search our sample particles, and we have to focus on it. We'll focus on it. Record. Okay. So I'm increasing the magnification. So I'm going to high magnification. Sorry, it is now low magnification 200. 200. Okay. I'll select the particle. Anyone? This one I can select. Okay. Now this is okay. So right now 15K is showing 15, 20, 25. Okay. And 30K. So if you see the okay. I was on out of the focus. Okay. So if you see carefully, you can see that there is some part. Oh, sorry. You can see the at the center. You can see some particles are visible, black spots. Okay. And these are the samples actually, particles. Right now I'm on 30K magnification. Okay. Now I'm increasing at 50 to 60K. around 40 to 60 kT is good for the taking the TEM image. So before taking the image, I have to align the beam and I have to do the gun alignment and the beam alignment. Okay, to focus the beam. For that, what I have to do? I have to do standard focus. There's some procedure we have to follow to centering the beam, focusing the beam. Okay. It is highly defocused beam right now. You can see. Standard focus. So what we have to do, we will go to the knob alignment, gun alignment. I'm turning on the gun alignment. So I have to go to magnification. Okay. It was on the low magnification. Okay, this one is the particle. Okay. So I have to do the beam centering. So we have to adjust the Z position. So we can see the beam, sharp beam, highly collimated beam. Okay. So yes. It takes time around 5 to 10 minutes to align the gun and beam. After that, we'll able to take the images. Okay. So now I'm turning on the gun alignment. So okay, now gun alignment is done. Now I'll change the spot size to the 7. And we'll do the same for the beam alignment. Okay. So our spot is not shifted too much. So it means it is good enough. I mean, almost beam is aligned. So using shift X, shift Y. So I'm shifting the beam spot along the XY axis on the fluorescence screen. I hope you are able to see. Okay. Now again I will repeat for the gun alignment. Okay. Now. So beam is aligned now. So at the 10K, I'll increase the magnification. Right now it is 15, 20K, 25, 30K, 40K, and 50K. Okay. So right now we are at 50K magnification. And I have to do the beam centering. Okay. So there you can see. Look at the standard focus. I have to move it to Z is defocused. Make it center. Okay. Yes. Now beam is at center. Okay. So now we can see we are ready to take the TEM image actually. I hope Camera is also ready. I'll just remove the fluorescent screen, and the beam will incident on the camera. And here we'll see the. So I'm inserting the. Okay. So see, this type image is coming. You can see. This is the particles are showing. So depending on the user interest, we move on the sample using this scrolling ball. We can move on the different particles, and we can take the image. So as I can see, it is we have to adjust the small Z so that can be that can get the image per image. Okay. So this is the you can see the scale. This is right now 100 nanometer. This length is 100 nanometer. So this particle is also around the 100 nanometer, which is a 0.1 micron size particle. Okay. This is actually gold particles. And this is the carbon ring, okay, on which the gold particles are distributed randomly. You can see. So brighter means this is here you can see that this is the brighter, this is the dark. So it's showing there is some thick particle is there. So electron are not enough passing as compared to this brighter region. That's why we are getting the contrast image. Okay, and this is the temp image actually. So if the uh, so user interest, based on the user interest, we take the picture. So for example, I'm taking one picture by reducing the brightness. It will automatically adjust it by the software. Yes. So you can see. So this is a. So you can see the how the particles are distributed. That token is already done. Okay. So again, so one user we have right now, Sambit. Okay. So Sambit, is it okay? Yes, sir. Shall I go other location to take the different particle image? If you, is it a gold particle? No? Gold particle? Silver particle. Sorry, gold and silver. Mix. Okay, mix of silver nanoparticles. So this is the TEM image basically. So I'm scrolling the this is ball to move around the image to see the different particles. Okay. So this is the TEM image. I'm taking 2-3 more images. Okay. So this is the TEM image. Just here. You can see. So actually, we adjust the focus and using some knobs to focus to get the good image. We adjust some shade and within the field of view, we adjust the focal plane, so that we can get the very good image. So I think it is good enough. So I'm just moving on the fluorescent screen. Okay. So at 50x, this one is we get. We can further increase the magnification to see the single particle. Focus on the single particle. Right. Okay. 60. You can see. Suppose this one we select the particle. See. Right now the scale is 50 nanometer. Okay. So again, I'm capturing. Okay. So okay, yeah. So I change the magnification. I need to do the beam centering again. So each time I have to do the beam centering. Beam centering. If I change the magnification, so I have to do the beam centering as well. So please focus on here on the fluorescent screen. So it is shifted, little shifted from the center. You can see now it is at center. Okay. Yes. Now moving on the camera. Yes, you can see. So bright in the at the edge you can see the bright lines is appear. Uh, White edge is appear. So I have to adjust the jets effects. You can remove this shadow type image. Okay. I'm adjusting this. Yes, it is okay. Reduce the brightness. Yes. So this one is the image you can see at the 50 nanometer scale. So so till now we have captured the 3, 4, 10 images, 10 images with the 100 nanometer scale and 50 nanometer scale. So by selecting a particular particle, we can do the uh, selected area electron diffraction to see the diffraction pattern. Okay, so we can select this one. For that, we need to insert the SA aperture of 20. Okay, increase the brightness. So okay, so I have to adjust also before inserting the SA aperture, small area aperture. We have to move on the 60 here. We actually it is independent of the magnification. Okay, so I can keep it at the 60K magnification. Now I'm inserting the. Usually we insert the 20 micrometer aperture. Okay, so you can make it center by inserting the another small fluorescent screen. Here is the second fluorescent screen, very small size fluorescent screen. I don't know whether you are able to see or not. A very small size, okay, around uh, 1 inch, something like circular fluorescent screen. So make it center, moving the aperture to keep the beam aligned with the aperture. I mean, I'm centering the beam around the aperture. Okay. So now I'm moving the beam to keep it at the center. See? Okay, this is that now. So now it is done. So as a aperture is inserted, so I'll keep this. Okay. Remove the small fluorescent screen. Okay. So from the magnification, I will move to DF. Okay. So you see this one pattern is coming, diffraction pattern. You can see. So from the magnification, I'm just moving on the. I changed the mode actually DFF mode to see the diffraction pattern. Here you can see. This is now at the center right now. So you can see. So now I'm opening the camera to see the set pattern, and let's start. Okay. See here you can see this is the variety of patterns. So this is circle. You can see the rings, right? Here you can see variety. Okay. From depth to magnification. Here you can see the set patterns. So selected area, electron diffraction. So from this image, we can calculate the interplanar spacing. We can identify the phase of the crystal, right? Okay. So by just measuring the radius from center to, actually we have to draw the circles, concentric circles, right? Using these patterns. Okay. And the different R1, R2 will get the radiuses. And from that, we can calculate the d-spacing, corresponding d-spacing. Okay, so this is the set pattern. First one is the TEM imaging, second one is the set pattern, and third one is the HRTEM, high resolution. It means we'll go up to 800K. We'll try to see the atomic arrangement. Okay, we'll go up to the atomic resolution. Okay, now come to the. Okay. So for that, we have to increase the magnification. So I'm removing the SI aperture. Okay. So now, right now it is 200K. I have to do the beam centering each time. Whenever I have to change the magnification, I have to do the beam centering as well. Huh? Outside the sample. Yes. Standard focus. Yes. Now our beam is at the center. Here is the a dark spot, black spot at the center of the this fluorescent screen. So I'm just focusing the beam, this electron beam at the center. Okay, so this is what I'm doing actually. So right now by moving the XY, I can move our electron beam. So right now the beam is focused on this black spot, okay, which is at the center of this fluorescent screen. It means the beam is at the center. Okay, so I'll set the standard focus. Further, I'll move. So I'll do the image bubbling and ST bubbling. Okay. So in the image bubbling, you can see the image is moving, is vibrating like motion is happening. So I have to minimize it by moving the jet. So here you can see now it is reduced. Optimum jet we have to fix so that the minimum motion appears. So image bubbling is done. Now I'll do the ST bubbling. Here you can see contracting and expanding. Reduce this one by using ensure we can insert the small fluorescent screen, this one. So it takes a bit time to focus. Yes. So ST bubbling is done. Now again I'll use the magnification. I'll go from 200K to 400K and we'll repeat the same thing. I'll do the beam centering and the HP and image bubbling. Check, see, now the beam is shifted from the center. You can see. So again I'll press the standard focus and we'll move the, I'll bring the beam at the center. Okay. Yes, now the beam is at the center. Now I'll do the image bubbling. So by moving jet, I can reduce the zigzag motion. Yes, this is the minimum. Okay, now I'm going to do the HT bubbling. You can see this HT bubbling we can minimize using defects and FI. Yes, it is contracting at the center. Okay, and expanding from the center. Okay, so this one is also done. Now further I'll move to 800K magnification and I'll yes. Now it is at center. It is at center. Now I have to do the image. Now it is reduced. Okay. Now we are ready to take the HR10 image. So at 800K beam is focused, and now I'm turning on the camera. I'm just removing this fluorescent screen. So this okay. Now just focus on the monitor. So here you can see some patterns like I don't think it's visible to you or not. See? So atom kind of arrangement, you can see the atoms arrangement. And if you see the scale, this is 10 nanometer. And here you can see dot 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 patterns. Atom is arranged. How the atoms are arranged. Here we can see the lines. These are the orientation with the different orientations. So this is the HR10 image. right now it is showing good image. Actually, we are getting good image. So I'm capturing it. Okay. So let me show you the image. See, please focus on the image. So this is the HR TEM, high resolution TEM image. Here you can see how the atoms are arranged. These are the lines. These are the lines. These are the lines. Here we can see the grain boundaries. Different orientations we can see clearly. This is the raw image. After processing this image, we can get the very good image how the atoms are arranged. Okay. So this is the HRTM image. So far, any question? Hello? Hello? Hello?
Yeah, are there questions from audience? Anurag, I think you can continue this. Yeah.
Okay. Okay. Okay, sir. So we'll take two more images with on the different location. See here we can see the very good image we are getting. So I'm reducing the right field. Yes. Going further, one more image I'm capturing. Samvin, you want more images, different location, or is it enough? Yeah. Enough. Thank you. So this is the these are the TEM image chart TEM images, and if time allows, so I can go for the EDEX. Sir, so this one is the third part. Uh, this is a chart TEM, and now we'll going on to EDEX for the elemental analysis. What elements are present. So this TEM image said and HR TEM image will give the structural properties, size, and all these things, but it is not confirming what elements are present in the sample. So we'll do the EDEX for the elemental analysis to confirm the what elements are present. Okay. So for that, I need some little time to go to the EDEX mode. So I'm just turning off the electron beam to ready the EDEX mode. Okay, so I'm selecting the okay. So I'm selecting project 1. I'm closing this setup. I'm opening the PL aperture. Okay. Now I'm going to operation, and from TEM operation to scanning operation. The operation is changed. TEM to so the aperture is to remove. Now I have to go to scan. I have to select the spot. I have to select the spot. And circle and circle. Okay. Is it okay? Now I have to turn on the beam. So, beam is turned on. I'm just removing this wall, beam wall, so that the beam can be incident on the sample. Now I have to press on. I have to press on the standard focus. So Binendu is helping me because there is some following steps. So we have to follow that for that. Okay, next one is go to scan. Now I'm moving toward the scan. Now I have to click on the ronchigram. Oh, sorry. I have to select this one. Yes. Now ronchigram is selected. The next one is so actually this is the DF aperture we have to insert now. Nothing is coming actually. We have to turn on this one now. TL aperture removed. Okay. अभी इंसर्ट क्या करना है ऐसे I'm not getting that on Chigami image now. So please give me time. Sorry for that. Go to the next one. This one now. Image should become. This one is coming. Okay. So we have to move. How move? So this is the turn on PLA. So I have to turn on the PLA. And now I have to move the DFF device to make it center. Okay. So ronchigram image is coming. Now this is at the center. We have to move edge of the sample, right? Yes. Here we are. Okay. Now I have to insert the CL aperture of 40 micrometer. Yes. Okay. This is shifted. So I have to make it. I have to bring it at the center. So moving. It's going up. Okay. Now, sorry. Now we are at the center. Okay. Now next. Now I have to insert the DF aperture. Now I have to select the ronchigram. Huh? Okay, upper screen. Now bring the image center by scrolling button. Okay. So these are this is our sample actually. Okay. Yes. Adjust the brightness to gain or offset. So we have to reduce it actually. Detector gain. Hmm? Now, this is the detector gain knob, and this one is the detector offset knob. I'm moving, I'm rotating this detector gain to reduce the brightness of the image. This one is the focus knob for. Okay. Yes. To see the contrast image, good image. So I'm moving the focus knob. I think this one is okay. Hmm. Then A to Z. Now come to this software, AZ Tech software for index analysis. So project is open. Now go to the next step. Now I have to ready the new project is done. That part is done. Now I'm coming on the detector. Here we can see the detector, EDS detector. So I have to click on the operate mode. It will take some time to actually it will cool the detector. Okay, after cooling, it will ready for the taking the data, right? So it will take time, little time. Mm, how much? Around 2 to 3 minutes. Okay. So let me show you the detector one. We can we turn on the light now? Shutter is closed, so we can turn on the light actually. That one, yes. So this is the ADEX detector we made from the Oxford instrument. So it will what it will do actually. ADEX is the energy dispersive energy dispersive X-ray diffraction, not diffraction, sorry, energy dispersive electron spectrum, EDS. Okay, so this is the EDS detector. It will go near to the sample grid. Okay, and will detect the X-rays, right? It is showing cool. When it will be ready, it will show the cooled status. So now we can insert this detector in. So moving in, near to the copper. Okay, moving in. Activity is moving, not moving. Okay, now it is moved. Fully inserted. Status is showing fully inserted. Now, okay, so this thing is not required. So right now magnification it is showing 40,000, and here this turn on. We have to ensure this boss will be matched. Now, okay, so now I have to go to on mapping. Where is the mapping? Yes, I have to go to on the map. I have to scan image. So it is already selected, and now it is selected the area. This is the sample area which is selected. So it's area mapping. I'm doing the area mapping, not the point mapping. The currently project contains the data that was previously acquired. Okay. So new data I have to create. We want to acquire the image of this type. No. Start. Okay. It is happening actually. Where we have to select actually, na? I'm come back to the scan. So this one is completing actually. Electron image store is taking. Got the map electrical square. This one, no? I think this one is already okay actually. Start. Okay. Okay. So image scanning is start. So this one is copper. This is sulfur. Fluorine, Cl, Au. Okay. Variety of elements. So in variety of elements are coming. So but our interest is on gold and the silver. Oxygen, fluorine. Okay. So right now what we are getting. So these are different. See, you can see that this is the image for the copper where the coppers are present. Okay, on this sample area. This is the sample area, and it is start scanning and acquiring the data and observing the electrons. Sorry, X-rays, corresponding X-rays of corresponding element, X-ray of the corresponding elements. So right now it is showing the where the how the CU K alpha one is the obviously um, uh, K alpha is the X-ray of the copper, and where from which area it is showing. So we can see the distribution of how the copper particles are distributed toward the area. This one is the Cr, this one is the Au, and this one is the oxygen and sulfur, chlorine. So some are coming. We are not sure they are even they are present or not. So we can exclude that element, and we can include only those elements. Those are our are in our interest, right? I mean, since we already prepared the sample and we have idea what are the elements are present in the sample. So we'll keep only that elements, okay? And how they are distributed, we can see. Okay. Now coming on the point and ID. Okay. Now predefined element. So I'm defining the what are possible elements are present. One is the AU. Where is the AU? AU. So I'm including it. Okay. And AG, including AG and oxygen. Oxygen. It will obviously it will form the oxide and chlorine and some bit. That's it. Yeah. So copper is also present. Carbon is also present. So grit is made of the copper. So we will get the copper. Okay, trace of the copper and the carbon as well. Film is carbon. So we are not interested on that one. Okay, so now next one. Now we have to go to the map. Okay, I'm moving on the map. Where is the construct the map? Construct the map. So our interest, we have to include now. So I can change in weight percentage, right? Weight percentage is already on the weight percentage. So I'm including the AG, AU, right, and oxygen, fluorine, and that's it. And copper is we are excluding the copper, है Okay. So it will take time to map. It is scanning actually. It is already around time is around 4. So it will take time around 5 to 10 minutes, at minimum 5 to 10 minutes to complete the scan. Yes. So I can, so what right now, what can I do? I can show the results, old results. So you can get the better idea what type of data or information we can get from the IDEX. So I'm showing you some big data. This is the data, actually reports. Yeah, yes, this one is a report. So here you can see this is the area we were selected in the last time, and here you can see the red spots. Red spot, it is showing oxygen, how the oxygen is distributed here, right? And the orange one is also present here. Orange particles also distributed here. So AU is the orange one, right? So red, these are the reds, and orange are also overlapped and random. These are the randomly distributed actually. You can see these are orange, red, orange. Okay, so in this sample only gold and the oxygen were present in weight percentage 50.8 and 49.2. And here you can see how they are distributed in the different energy. Okay, so this is the result. Yes, you can see individually. This is for the red how the oxygen is distributed, and here how the gold is distributed. This is a scale of this is an image of the sample actually, and the gold and the oxygen, how their atoms are distributed. So this is the ADEX analysis actually to ensure the what elements are present in the sample. Okay, so it was already running now. It is running. So I can we can get the acquired map data, right? I'm moving on the acquired map data, and I can stop. If we change the location now, we'll get the better result, right? Project 1 is saved. Okay, so I'm removing the position. I'm just removing the detector. So by taking it out, okay. So the mapping is EDX mapping is we do like this actually, and these are the things we do in this HRTEM facility. So far, any question, please ask. Am I? Hello?
Yeah, Anurag, they're actually very
Sir.
conservative, so they're not asking questions normally.
Okay,
You can
sir.
ask them questions.
So,
Okay, you can ask them questions and they will answer.
so what do you understand about the start time facility? So TEM site. So you can go that iSTEM site and you can book your slot using iSTEM site, and for your sample you can take for your research also, obviously research. Okay, so this is the one information I want to tell you. And another thing is about the HR10 imaging, and this is very costly equipment, and facility is very limited across the India. So you are welcome. And about the theory and obviously I told you the very basic things of the TEM imaging. So it has more potential, and the different analysis like LSF, other things we can do. Dark fielding. Right now, till now, I have done only the bright imaging. One thing only the set, which is a dark field. So it has more potential, and I mean it has more features to take the to do the different analysis also, obviously. So these are the basic model actually we have in our department. So TEM and SED, HRTEM and EDEX analysis you can perform here. Thank you, sir. So I think I don't want actually to ask anything from them. Hello?
Yes, that's fine. That's fine. Let me just take a call. Sorry.
So, sir, shall I leave the meeting? Mode is changed. I can turn off the beam. So you can remove the इसको कर लेते हैं
Acha,
sir shall I leave the
Anurag,
meeting sir
Anurag,
sir
what you can do is
sir
while you have shown the process, how did you start the
hmm.
setup? Basically,
Hmm.
parking the setup is also important. So few steps that you are doing after this, you can implement or tell them and then close the meeting. Did you get my point?
Okay, sir.
So basically, even shutdown. So probably more experiments would be done. So vacuum is anyway
Yes, sir. Yes,
maintained
sir.
24/7 inside the column.
Exactly.
Fine. But
Exactly,
then
sir.
there is
Exactly.
some basic thing related to how to remove the sample
Yes,
and
yes. I am
then
going
how
to.
to park the system. So that you can just say
Okay.
that we simply follow the reverse process, right? Basically, that's what we do, right? While loading the sample,
Okay.
we follow a
Okay.
particular
Yes, sir.
process. So we are just following the
Right.
reverse. And the load lock is used just to ensure that the actual column vacuum is not affected in any way,
Yes.
right?
Yes,
Yeah.
sir. So, right, sir. So now the next step is to park the system. Means we have to remove the sample, right? So, hmm? So for that we need to neutralize the stage. So here we have to click on the stage neutral. So now it is done. So now we can remove the sample holder from the chamber. So I'm opening it. Okay. So, so, so I have to move it. Okay. 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 So we are just following the reverse process as we inserted what process we followed to insert the sample holder. We are just doing the reverse. We are just following the reverse process. So half we have just removed. Now the sample holder is on the specimen chamber. Now what we'll do? We'll purge the nitrogen. Okay. So the specimen chamber increase. Okay. Vacuum will decrease. Now it is now okay na. So I can give the air, right? So I am giving the air that is obviously nitrogen and two. So here you can see increasing specimen chamber pressure. So here you can see the nitrogen is purging. So it will take time around 2 to 3 minutes. So sir, Ajay sir already told the vacuum, high vacuum is maintained from 24 plus 7. I mean, all the time vacuum should be maintained and beam should be on HP beam. We cannot we cannot HD beam off for the long time. It will affect the resolution. So usually what we do, we always turn on the electron beam. We maintain the high potential, high field, 200 kV. Okay, all the time. Huh. So the nitrogen purging is completed. So now we can remove the sample holder. Here you can see it is easily removed. We can easily remove this because there is no vacuum. Sample holder is removed. Now we close this chamber and we have to remove the grid. So yes. Okay, so we just remove the grid, okay, from the holder, and we can, yes. Now the removing of sample grid is done. Now we can keep this holder with us. And so, so done. So you can see the vacuum is maintained. It will maintain for the beam. So no, and usually what we do for in 2 weeks we do the backing for to maintain the vacuum of the column, and it takes around 72 hours, right, for the backing. And in month 2 month we calibrate the camera in the dark field. So yes, I'm removing the. Oh, we already did remove the camera, and we have to save this data. So save as, going on some with, it is already saved. Okay, so we can save this data like this, and HCD heat. Okay, so initially what we did, we filled the liquid nitrogen. So we have to remove that nitrogen. So we have to heat that area. So what we called it the ACD heat. So I'm going to maintenance. Okay. So I have to remove all the nitrogen gas using this heater. So this is a kind of heater, you can see. So I have to insert this heater. Okay, so now I have to start the ACD heat. So this ACD heat will heat the area and it will evaporate the nitrogen, liquid nitrogen. Okay. So I'm starting the ACD heat. Are you sure you want to start the ACD heat? Yes. It is already removed. Real aperture. Now you can see ACD heat is on and the nitrogen will evaporate. So these are the procedure we followed. Huh? Okay, DF aperture is not inserted. Already removed. Yes. So, sir, hello. So these are the things we do to close the, to complete the measurement things. Nobody is responding. Sir, thank you very much, everyone, for giving your time and keeping
Yeah, so
patience
let us thank Dr.
to listening us.
Anurag for, let us thank Dr. Anurag for the nice session. Like this is the electronic applause. And also let us thank
Thank
Bidindu ji. Like both of them have
yes,
nicely managed
yes.
this session. Thank you so much. So we'll
Thank
close
you so
this
much,
session
sir.
now. Yeah, sure. Thank you.
Okay. Thank you, sir.